Okay, this next problem called defining similarity through angle preserving transformations. This one's tricky. I worked through it several times and made little mistakes here and there as I've done it myself. But basically what we're going to do is I'm going to take you through a few of them so you can kind of see how it works. So we're trying to determine whether or not these two triangles are similar. And in order for them to be similar, there needs to be a sequence of rotations, reflections, translations, and or dilations. So rigid and or similar translations that are going to transform, is going to map ABC onto DEF. So the first thing I'm going to do is I'm going to rotate, because I can see this right angle. It looks like it could map up with DEF. So I'm going to try rotating this. So I come down here. I'm going to rotate around about this point right here, which is 7, 6. So I put that in, 7, 6. I'm going to rotate it up 90 degrees. So that's a negative 90 degrees is how they do it here, right? And then I'm going to translate. I'm going to move B over to the left. I want to go directly to the left. So there's no shifting here up. It's going to stay there. But I need to go from 7 over here to 5. So that is a total movement of 12. Oops, but it's a negative 12, right? It's a negative 12. And now I need to dilate, and I'm going to just look at this length here, right? So this is going to be a dilation. It's going to be, the center of the dilation is going to be right here, negative 5, 6. Excuse me. A negative 5, 6. And my dilation, well, remember, it's new over old. So my new measurement is 2 lengths units here. I can see 2 units that I go here. And my old was 4. So 2 over 4 is 1/2. So I put 0.5. That's a half. And boy, it doesn't look quite right, does it? See, this is where it doesn't look correct to me. It looks short. So I'm going to say they're not similar. I've got this leg matched up pretty darn right. And that leg is short. And this angle is a little goofy. It's a little goofy, so we'll say that they're not. And that was correct. Okay, so that's how that's done. Let's try another one. Triangle quadrilaterals A, B, C, D, and quadrilateral E, F, G, H are similar by looking at a sequence of rotations, reflections, and translations. Well, I can tell this is kind of, my two long sides. This almost looks like a little bit of a rectangle to me, but I know it's not. But these two long sides really stick out point A. So if there's going to be a chance of this mapping, A is going to get over here near E. So what I think I'd just do is I'll start by just seeing, maybe I can just map C up. Well, let's see. Is there any point that could map up easily? Could A get mapped up to F? No. B get mapped up here? Oh gosh, that's kind of ugly. Well, let's just try that. Let's put B over to here, which would be a translation. We would need to go, what is that? 10 units to the left, so minus 10, and then up. Oh, it's not a full 10. It's 9.5 units, and then up 2. So let's try a translation where we're going to go minus 9.5, but up 2. Okay, so now what I think I'll do is I'll try to reflect it over this line, and let's just get it looking like it's in the right general direction. Let's just see what happens. So this line right here, so we're going to do a reflection over this line, and this line is, I could say, I could pick a point here at negative 7.5 and negative 4. So negative 7.5 tab negative 4. You can press tab and it moves you through those fields pretty good. Okay, and then the next line is going to be, also negative 7.5, and let's just put 8 up there. negative 7.5, and 8. Okay, hey, now we're kind of in business, right? Because, you know, I can see that I've moved here, right? And what I did was I went down 1, 2, 3, 4, and over 1, right? So if I did that, how many more times do I need to do that? 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. So if I were to repeat this 3 times, so I think I could dilate this from point F, right? Point F looks like it is, what was that again? Negative 7.5, and that's positive 3. That's point F. And we've done this once, but we want to do it 2 more times, so that we want a total measurement of 3. We want 3, and there we go. We've mapped it up. So we can say that they are similar. Okay, one more I'll do. A triangle went under a translation, that's a rigid, a rotation, that's another rigid, a reflection, that's another rigid, and a dilation. Aha. So it is similar. When we know if it went through rigids and a dilation, then it's going to be similar to the original one. It says below is the result of these transformations. So once it was done, we know we ended up with this triangle here where AC was 9, BC was 4.5, and the measure of angle C was 90. So which of the statements are necessarily correct? The original triangle was a right triangle. Well, this one is, and similarity transformations preserve angle measures, so it has to be that the original triangle was a right triangle. It says the original triangle had one side twice as long as the other. Ah, that's important. Look at the ratio here. 9 is to 4.5. That's twice as long. And remember, similarities, now this is something you may not be aware of, but similarity transformations are going to preserve the ratios of the original side length. So 9 to 4.5 is 2 to 1, right? So the original triangle also would have had to have had one side twice as long as the other. So both statements are necessarily correct. Okay, and that is where I'll stop.